Today I'll be talking about the Arndt-Eistert synthesis. The Arndt-Eistert synthesis is a series of chemical reactions designed to convert a carboxylic acid to a higher carboxylic acid homolog, containing one additional carbon atom. The synthesis allows for the formation of a homologated carboxylic acids or the derivatives by reaction of the activated carboxylic acids with diazomethane and subsequent Wolff rearrangement of the intermediate diazoketones. So in the mechanism, you will first start with a carboxylic acid that reacts with the SOCl2 HCl. In this, the Cl will then attack the carbon and the double bond will then be brought up to the oxygen. This will create their first intermediate, which is the chlorosulfite intermediate. And then the carbocation will be brought down to this bond right here. This bond will then go to the bond against the oxygen and sulfur. And the bond right here will then be brought to the chlorine. This will form the acyl halide, and the acyl halide will then react with the diazomethane to create the next intermediate, which is the diazoketone. This will then be rearranged and form this product right here. This will then be rearranged again and reacted with the HCl CH2N2. In this step, the reaction with the diazoketones occurs at a high temperature, so the diazoketone is able to form many resonant structures right here in step 4, and this is the next intermediate. This will then react with the AgO and nitrogen 2. This will then form this compound right here, which is the next intermediate. This will be rearranged, forming the next intermediate, which is compound 6. This will go through hydrolysis and then form our final product. And this will be a carboxylic acid with an additional carbon attached to it. So in the reaction coordinate diagram, there will be 3 intermediates and 4 transition states. So the reactions will then start here. Both the reactants and products will be near the same energy, just because the functional group did not change other than the carbon atom being added, so they'll be relatively the same energy. So the reactants will go to the first transition state, and then the first intermediate would be the compound 2. This will then go to the next transition state, and then the next intermediate will be the acetoketone, and then go to the third transition state, and the third intermediate will then be compound 6. And it would go into transition 4, and then this would end up to the products. So this right here is an abbreviated reaction coordinate diagram since the mechanism is so large. If I was to draw the full thing out, I would also add the other intermediates. This would include the chlorosulfite intermediate, compound 3 intermediate, compound 4 intermediate, and then compound 5 intermediate. So the next 2 questions is how might you speed up the reaction? To speed up the Arndt-Eistert synthesis, the temperature can be increased throughout the process, especially in the reaction with the diazoketone and HCl with CH2 nitrogen 2, since it already occurs at a high temperature. Another way to increase the rate of reaction is to add more concentrated reactants to the system. So what would you predict in the changes in the spectroscopy data to be? So when looking at the infrared spectra data, there would be a little change from starting material to product because the major functional group, carboxylic acid, does not change. The only change in the starting material and product will be the presence of an additional carbon in the final product. So by looking at the carbon MMR for the Arndt-Eistert reaction, it will help take a closer look at the structural differences of the carbon chain from starting material to product. When looking at the carbon MR for the starting material, carboxylic acid, there will be 2 peaks around 170 to 175 ppm and 9 ppm. Looking at the MR for the product, the major differences would be the presence of an additional peak on top of the 2, which would be around 27 ppm. And this is due to the addition of the carbon. So an example of a recent study is the title is Improved Arndt-Eistert Synthesis of a Alpha Diazoketones Requiring Minimal Diazomethane and the Presence of Calcium Oxide as a Acid Scavenger. This Arndt-Eistert synthesis method required minimal diazomethane in the presence of calcium oxide. In this experiment, the researchers looked for a simple anorganic agent that had effectiveness in scavenging the release of hydrohalic acid and thus getting the desired alpha diazocarbonyl compound as the only reaction product. The researchers tested the effectiveness of the calcium oxide as an inorganic proton scavenger and compared it to other commonly employed bases in organic synthesis. And the results indicated the superiority of the calcium oxide out of all the bases that were used in the synthesis and reactions. So the results of the experiments revealed that the simple protocol of using calcium oxide as a hydrohalic acid scavenger allows for an improvement of synthesis of aromatic and aliphatic diazoketones through the use of the Arndt-Eistert synthesis method. The use of this improved methodology allows for the possibility of reducing the reactive diazomethane, which is a great advantage for safer applications at a large-scale process, and this would help to apply green chemistry to this field of work. So this is my name reaction video. Thank you so much for listening.